Recording has started.
Hello everybody, my name is Chen Ziyu from Jojo Tech. Today I would like to give a talk about incorporating intrinsic flexibility effect into morpho-absorption property simulation at a low computational cost. To start with, let me first introduce the background for this project. So metal organic framework, which is MOFs, have been widely used in gas absorption. Separation and the capture of gases utilizing MOFs are challenging but promising. Uh, what is more flexibility? Compared to zeolites, morphs are flexible and have a strong influence on absorption properties. And there's mainly two types of flexibility. The first type is intrinsic flexibility, which includes atomic vibration and linker motions without volume change. And the second type of flexibility is extrinsic flexibility, which is triggered by adsorbate, temperature, pressure, etc. The bottom figure is an example of the extrinsic flexibility triggered by adsorbate. Some well-known morph properties, say breathing and swallowing, are all one of this type. So as you may know, previously, the extrinsic flexibility are widely discussed because they have a non-trivial influence on the morph absorption properties. However, these days, the intrinsic flexibility have also been shown to be important for morph absorption properties, especially when kinetic diameters of adsorbate molecules are comparable with morph pore size. To make several examples, Mayank and his co-workers examined the absorption of adsorbate in 100 moles as dilute and non-dilute absorption conditions, which show that the absorption and not-dilute loadings and selectivities can be significantly affected by this intrinsic flexibility. As you can see from the figure on the top, the axis is the ratio of the current constant from flexibility prediction and the current constant from rigid prediction. And you can see a large portion of the morphs actually are influenced by this type of flexibility. And to give a second example, like Parker and his co-workers found the intrinsic flexibility of morph have a non-trivial impact on surface activity absorption modeling. The figure on the bottom, the x-axis is the selectivity from rigid prediction, and the y-axis is the flexibility from flexible prediction. And we can see there's a difference between these two predictions as well. So after I introduce the importance of the intrinsic flexibility, let me introduce currently how we are able to model this flexibility. First of all, the quantum mechanism level simulations are not affordable for those type of flexibility modeling because the system is just too large. So currently molecular dynamics are used to model this. However, there's two major limitations for the molecular dynamics approach. The first one is reliable force fields are not always available. As you can imagine, to describe the movement of the framework, we need to develop a kind of very accurate force field, and those type of force field is not always available. And the second drawback is it takes lots of effort to build a model. Basically, you from a structure into a machine readable MD input file is not an easy task. So we are trying to think about a way that we can just try to model this intrinsic flexibility more at a lower computational cost and with a much easier implementation way. So we are trying to do this by starting with experimental information and build a model based on that. So what is available in experimental intrinsic flexibility? Actually, there's parameters named atomic displacement parameters, also known as atomic vibration parameters and thermal parameters, which is used to represent displacement ellipsoids. So the displacement ellipsoid is actually the description of how an atom vibrates around its equilibrium state. And this type of parameters is available in narrow standard C files and it's obtained from XRD techniques. So based on that piece of information from experiment, we are trying to build a model. So this model overall is based on the snapshot method. So the snapshot method is used to statistically assess the flexible impact, and it is a computational approximation to bring down the computational cost by separating framework movement and absorption process, which is validated and used by previous research. So this is really a computational trick to enable the modeling of flexibility in a practical way. The core of the snapshot method is to generate snapshots. So previously, these snapshots are generated by doing MD, but now we're arguing that we can actually generate snapshots from experimental crystal structure by using these parameters I just mentioned in the last slides. And the technical detail is we assume Gaussian distribution of atom positions. We fix hydrogen atom distance to heavy atoms be constant at experimental volume, and we correlate neighbor atoms by average displacement. And we rescale temperature from experimental data using Boltzmann distribution. And this flow is the illustration of the ellipsoid method. So the only input for this method is the experimental save file. And by going through the in-house Python code, we can generate a bunch of flexible structure snapshots. And these snapshots with its default setting will conduct GCMC for each of the snapshot. And the absorption property prediction with flexible influence can be obtained by averaging the GCMC result for each snapshot. So let me give a quick review and summary toward this model background and model implementation details. So traditionally, rigid structure is used to give the absorption property. Like the whole absorption property prediction is based on this single structure. However, previous research showed that the intrinsic flexibility have non-trivial influence on absorption properties. So basically, after taking into consideration of the vibration of ligand or the vibration of the atoms, we can see the pore size distribution actually changed. Like the pore size distribution for flexible snapshots are actually widened. So those those changing physical properties definitely resulting in a non-trivial influence on absorption properties in lots of cases. However, traditionally, to model this type of flexibility, we need to do the MD to describe the more framework movement, and it is not an easy task. So we propose that based on experimental information, we can have a new model that have a much lower computational cost by going through the generation step for snapshots in the last slides. And in terms of the simulation result measurement, we think quantitatively intrinsic flexibility is important if p-volume for one sample one-tailed t-test is less than 0.1 or greater than 0.9 for results from flexible snapshots and rigid snapshot. This is actually a statistic test, like to see whether the flexibility results are different than the rigid result. And quantitatively, if flexibility importance is less than 0.75 or greater than 1.25, we consider the intrinsic flexibility to be important. So what is flexibility importance? Flexibility importance is merely a ratio of the flexible structure absorption mean volume divided by the rigid structure absorption volume. So there's two standards for us to determine whether we should consider the intrinsic flexibility is important or not. From this slide, I will try to discuss the result for our simulations. So the first step after we develop a new model is to validate that. So of course we did that. Like we test the accuracy of our newly developed ellipsoid method for dilute and non-dilute uptake. We picked 20 random maps from COMB database to predict the absorption at dilute and non-dilute condition for 7 out of 8. We used both the traditional MD method and ellipsoid method to give flexible more framework absorption property predictions. In terms of the simulation result, first, according to MD result, intrinsic flexibility is important in 55 systems for non-dilute and 29 cases for in-dilute systems. And the prediction from the ellipsoid method are compared with the prediction from MD, and these two sets of predictions are qualitatively consistent in around 90% cases, and quantitatively consistent in around 40% cases. So let me discuss this consistency in my next slides. So I just picked 5 morphs example to show like what is happening there. So for the left figure is the non-dilute systems. Like all the blue points are the prediction of flexible importance from ellipsoid method, and the orange points are the prediction from the MD method. So you can see usually these two methods have a quantitatively consistency prediction in terms of like whether the flexibility have a negative influence on the sorting properties or have a positive influence on the flexibility properties. However, in terms of the quantitative prediction, sometimes there's a little bit deviation between the two methods. And figure on the right is the same case for the dilute cases, and we can also get the similar conclusion. So overall, the conclusion is that our model can qualitatively predict the importance of more flexibility on adsorption. And besides that, we also try to apply our methods on some other systems, which is ionized amplitude morphs, which we just picked for ionized amplitude morphs to simulate the adsorption isotherms, use both rigid structure and flexibility structures, and compare them with experimental observation. So for the figure A, we can see all the rigid predictions and flexible predictions are kind of consistent with each other, and are also very close to experimental observations as well. So which means that the intrinsic flexibility is really not important in these systems. And we can see for the figure B, all the rigid predictions are actually very away from this experimental observation, as is black dots in the figure. And our flexible prediction from our ellipsoid method and MD methods are closer to experimental data, but still there's a little bit deviation, which means that probably a more accurate method should be conducted to fully capture the experimental isotherms. And besides the morph systems, we also apply our methods on the morphosis material. And because our ellipsoid method can give a qualitative prediction of importance of more flexibility without using force field, and the access to reliable and transferable force field to morphosis material is very challenging. So we think this is our method is definitely suitable for the morphosis material modeling. So some simulation detail to be noted is that because none of the structure comes directly from experimental data, so the atomic displacement parameters are not directly available, and we'll tackle this problem by two approaches. First, if the morphosis material have a corresponding crystal material, the parameters will be learned from the crystal material. And if that is also not available, the mean placement from the morph system will be used and apply them onto this morphosis material. So here I just picked in PM3 as the example here. So we can see from this figure, the vibration parameters are based on MD result from COMMORPH and is averaged by Orton type defined by UFF, and the p-volume for the CH4 methane adsorption isotherms are all below the threshold, and which means there's no difference between flexible snapshot and rigid snap prediction statistically. And the flexibility importance is also between 10% differences, so overall intrinsic flexibility is not important for this case. However, in hydrogen adsorption theorem is another case which the intrinsic flexibility is important. So to give a summary, a method that can give a qualitative prediction of importance of morph flexibility on adsorption without using force field for morph is developed and validated using 20 morphs from COMORPH database. And we have applied the new method on unappeared morphs and morphism material. And we argue that our new method can be used for newly synthesized material, and it can rapidly assess if intrinsic flexibility matters for potential adsorption application. And before building a complex model, our model can give a general idea of whether it is worthwhile or not. And also for material where access to reliable or transferable force field is challenging, and that is cases where our model is also very powerful. So I would like to thank for the funding source and thanks for the group members within our group. And I would like to take any questions in the live chat section or the blue jeans or the the online sections. Thanks.